Our next speaker, Gilles Dowek. I'm very sure I pronounced it absolutely wrong.
No, it's perfect.
It's really? Okay.
I'm sorry.
He's a researcher at ARENA, at the Ecole Normale Supérieure, Paris-Saclay. He's interested in the formalization of mathematics, in proof processing systems, in the physics of computation, in the safety of aerospace systems, and in the epistemology and ethics of information. His books, Le Métaphore du Calcul, 2007.
No, that's not metaphor, it's metamorphosis.
Translated as, oh, thank you, that's the translation as Computation, Proof, Machine, Cambridge University Press, 2015, this is really impressive, had been awarded the Grand Prix de Philosophie of the Académie Française in 2007. He's a regular columnist for Pour la Science and the Le Monde. He's going to talk about that computing is very often viewed as an inferior way of thinking, unable to take contexts, reflexivity, emotion, ethics, and as such into account. This raises philosophical and scientific issues. Please, Gilles.
Thank you. So I understand that when it will be 8 o'clock in this clock, I should stop. My first issue in preparing this talk was to understand the meaning of the word sophistication. And as you know, this word has many meanings. And the most obvious one is that something is sophisticated. So the sophistication is a character or something which is complex, elaborate, and so on. But also the word itself reminds us of the sophists. And sophists themselves, the word sophist itself has several significations. The first one is to the historical one, where the sophists are a community. Actually, they are a professional community of teachers in the Greek antiquity. And also in a more modern, contemporary use of the word, sophist is someone who tells sophisms. And sophisms are argumentation that look rigorous, but that are fallacious, misleading, deceptive, and mostly because they are over-sophisticated, over-complex, over-elaborated arguments. And I will use the word sophistication in this meaning. When Vera invited me to this meeting, thank you, Vera, for the invitation, we had a discussion, and she raised the question whether there was or not in our world a trend to no longer trust in and engage in real arguments, but rather to perform as sophists. So what does it mean? To perform as sophists on the basis of calculation, on the basis of using algorithms. And this is the question I wanted to address. And I have to tell you already that I don't know, I don't have an answer. But this question presupposes that it would be to perform as a sophist if we used computation. And let me give you two examples where instead of truly trust and engage in real arguments, the use of algorithms could be seen as sophistic performance. An algorithm, I will use the word many times, and an algorithm is just a cooking recipe that is useful to solve a problem. So for instance, if you want to search for a word in a dictionary, there is an algorithm for that, and there are two actually, or many, but two are interesting. The first one is to look if the word you're looking for is the first word in the dictionary, then the second word, then the third word, and so on. And there are something like 60,000 words in the dictionary. It may take you something like 60,000 seconds or half seconds to reach the word that you are looking for. But there is also another algorithm which is called the binary search, where you open the dictionary in the middle and then you compare the word with the word you have in the middle of the dictionary, and then you throw away half of the dictionary and you repeat the algorithm with what remains. And in this case, instead of comparing the word to 60,000 words, 16 comparisons are enough, because 2 to the 16 is 65,356, which is more than 60,000, which is the number of words in the dictionary. So you see, it's just a cooking recipe how to find a word in a dictionary. And let's take two examples. The first example, which is very often given, is whether a judge should apply an algorithm, or whether a judge could be replaced by a robot implementing an algorithm. So I will give you an example of an algorithm that the judge could apply. So if you steal a bike, it's 1 week in prison. If you steal a car, it's 1 month in prison. If you steal a truck, it's 1 year in prison. So for the judge, the job is very easy. You have a case. So this guy has stolen a car, so it's 1 month. That guy has stolen a bike, so it's 1 week. That woman has stolen a truck, so it's 1 year. And it's very easy. And as you see, the judge himself or herself does not need to be trained very much. She only needs to learn the algorithm. And you can even replace the algorithm with a robot or with a computer, because this kind of algorithm, computers are very good as using them, applying them. But of course, this is not what a judge is. A judge is supposed to take into account the childhood and the reason why the bike has been stolen. So if you have stolen a bike because you had to escape from an earthquake, for instance, or, well, it's not exactly the same thing as if you have stolen a bike to rob a bank. So I don't know how you can rob a bank with a bike, but let's assume you can do it. So it's a very complex situation that you have to take into account, and it's not just an algorithm you have to apply. And of course, I could not resist to transpose this example to architecture. So an architect could receive a client and just ask how many rooms do you need, how much money do you have, and then applying an algorithm, you get the house or the home you are going to build for this client. So if the client has 10 children, you must have 11 rooms. If the client has 2 children, you have 3 rooms. And then, depending on the budget, you can use concrete or wood or cardboard to build the house. And again, it's not what architects do. Architects have imagination. They are creative, so they try to build each house in a different way, not just applying algorithms, but doing something else. And if they did not, then we could easily replace the architects by a robot or a machine or a computer, and then we could call these architects a sophist, exactly like the judge before could be called a sophist if she used an algorithm, just because her action, her performance would not be real. There would be no engagement of the judge. Okay, so here we have this implicit assumption that to use an algorithm to calculate is to perform as a sophist. And the consequence of this assumption, of this hidden assumption, is that there are other things that we consider as not being the application of an algorithm. And I can quote a few. So there are 4 kinds of arguments that you can find. The first one uses a keyword: creativity, imagination, intuition, emotions. And the idea is to explain here that we are gypsy children. Okay, you know, love is a gypsy child. And like all gypsy children, we have never heard of law. And this is, here we have the idea that let's use intuition and creativity to say that there is something more that when in the algorithm that we are able to perform. Then there is another distinction between human beings and machines, computers, algorithms, which uses different set of keywords, which are free will, disobedience, and an algorithm is not able to disobey from the rule, and we are. And we can disobey because we have free will, and this is another difference between us and the computers. Then there is a third line of arguments where the keyword is determinism. So in our life we have chance, luck, randomness, chaos, and algorithms do not. They are fully deterministic. So in fact, it's not completely the case because many algorithms are non-deterministic, but I will discuss that later maybe. And the fourth line of argument is centered on the keyword, the soul. So we have a soul, and the computers do not. So this is another difference. So you see that in our popular culture, we have a lot of reasons to think that there is, on one side, human beings, on the other, algorithm, they have nothing to do. And whether you're an artist, a philosopher, or clerk, a priest, then you will put more the emphasis on creativity, free will, non-determinism, soul, the existence of a soul. And these kind of arguments are interesting because they come in contradiction, or at least in friction, with another thread of thought that started almost a century ago. And this is what I want to confront, these 2 points of view. One point of view where it's obvious, there are empirical evidences that we are very different from computers. We cannot be simulated by algorithms because algorithms have no creativity, free will, and so on. And another thread of thought that is much more skeptical on this idea and much more careful to not jumping to the conclusion that fast. So to present you this line of thought, I have to tell you a very long story that starts in the 30s of the 20th century. And at that time, as Nicolas explained very well, for some reason, the logicians were looking for a precise definition of what an algorithm is. And in fact, it's fair to say that everything started from this place, at least this city, because the first definition of what an algorithm is was given by Kurt Gödel, the famous logician, Austrian logician, but he's not famous as an Austrian logician, he's famous as a logician. And in an exchange of letters with another logician, Jacques Herbrand, they gave the first definition of the notion of an algorithm. Here, they try to give a better definition than just an algorithm is a cooking recipe to solve a problem. And in particular, they wanted to be able to classify the problem that could be solved by an algorithm and the problem that could not be solved by an algorithm as the Entscheidungsproblem that Nicolas presented just before. But at the same time, other logicians in the world, Turing, Alan Turing, Church, that you mentioned as well, Newman, Kleene, gave other definitions. And something happened at that time that happens very rarely in science. So it's almost a miracle. So what happened was that all the definitions that had been given by these different people in different places happened to be equivalent. So let me just give you the names of these definitions. In fact, each definition kind of defines a language in which you can express algorithms. And it's what we would call now a programming language. And I will just give you the names of these programming languages, not because I want to explain what each of them is, but just because you may have heard the names, and the names are very poetic. So for Herbrand and Gödel, algorithms were defined by recursive equations. For Turing, they were defined by a Turing machine. For Church, the most poetic name, lambda calculus. For Newman, they were defined by rewrite rule that we discussed before in the meeting. For Kleene, by computable functions. For Post, like with post systems, so it's not that poetic. When you define such a language in science or anywhere, usually you get a language, but there can be a better language and there can be a worse language. So take the example of music. There is a notation for scores, the language of scores. But as you know, the language of scores makes composers unhappy, and they always want to add something. So if you start with crotchets and quavers, which are also called quarter notes and eighth notes, then you're unhappy because if you want to take a quarter note and cut it in 3 parts, then you cannot express that with quavers or crotchets or whatever. You have to introduce a new notation, which is a triplet. But even if you introduce a triplet, then there are glissendi that you cannot express, so you have to introduce something else. And for instance, György Ligeti completely dropped the language for scores and invented a completely new language. And there are things you can express in the language of score that you cannot express in the language of Ligeti, and things that you cannot express in the language of you can express in the language of Ligeti that you cannot express in the language of scores, and so on. But in the case of algorithms, there was a kind of miracle that although all these languages had been defined independently one from the other, each time you had an algorithm expressed in one language, you could translate it into any other. And at that time, the logicians, and in particular Gödel, pointed this was an exceptional situation. And it led them to think that they have found a notion of algorithm that was absolute and unsurpassable. So they said, okay, we got it because of this empirical evidence of the equivalence. This idea that we will never be able to build a better language, a language expressing more algorithms than lambda calculus, Turing machines, post systems, and so on, is called the Church-Turing thesis. And before 2012, it was called Church thesis. And if you read my old books I wrote in the 20th century, I used Church thesis. But in 2012, it was the century of the birth of Turing, and suddenly the Church thesis became the Church-Turing thesis, which is probably fair because Church and Turing had written papers on this thesis roughly at the same time. So not only the notion of algorithm was discovered independently, but even the thesis of the equivalence of these definitions was discovered independently. Okay, so at this point you say it's a very beautiful story, but what is the relation with sophistication? Okay, not so fast. You have to listen more about this story. At that time, in the 30s, we had programming languages. We had languages to express algorithms, but we didn't have computers. The computers were built in the 40s, so 1 decade after that. And when the first computers were built, like the Manchester machine or the ENIAC or whatever, or the K3, okay, these are names of the first computers. Of course, we noticed once more that they could express exactly the same algorithms that could be expressed by Turing machine, lambda calculus, and so on. And they could not express more, and they could not express less. So it was another language. Now it's a mechanical language. It's not really language. It's a language implemented in silicon. It was not silicon at that time, but never mind. And it did not surpass any of these languages. It was not surpassed by any of these languages. But the construction of these computers led to a transformation of this Church-Turing thesis. Instead of saying that all these languages were equivalent and that they could not be surpassed by any other language, the thesis was transformed into another form that we call the physical Church-Turing thesis, which is that no computing machine will ever compute more algorithms than the computers that we had at that time and that we have now. They are the same. And it looks like a thesis about machines, but in fact it's a much deeper thesis about all physical systems. And this is maybe the point which is slightly difficult to understand in my talk. I was speaking of machines and computer science. Now I'm talking about physics, any physical system. But the explanation is not too difficult. Imagine you have a physical system that could not be computer simulated. Okay, let's take an example. If you take a metal wire and you bend it and you give it the shape that you like and you drop it into a mixture of water and soap, and then you put it out of the soap, you get a soap film on the wire. Okay? You have this in mind? Okay, take a circle first, you put it in the water, then you take it out of the water and you have a soap film. But maybe you didn't want a circle, so you bent your circle in a very crazy way, a very baroque way. But you do it again and you get another surface. Okay? So this surface, they are called the Plateau surface because of the name of Joseph Plateau. Okay? And they are minimal surfaces. So they are the minimal surface that you can build with the limit condition which is given by the wire. The limit of the soap film is a wire that you have bent in a funny way. And this is an example usually architect-like, because you see that the shape of the wire generates the shape of the soap film. So of course, soap film are not very good for building houses, churches, universities. In soap, it wouldn't work. But they are very good for building shapes. And once you have the shape, you can do whatever you like with the shape. Okay, so then you can ask, is it possible to use a computer and to compute the shape of this soap film, knowing the shape of the wire? Maybe, maybe not. So if we can simulate this system, if we can computer simulate this physical phenomenon of the soap film, we say that we can simulate it. And if we cannot simulate it, maybe we cannot simulate it, then we have a kind of physical phenomenon that we cannot simulate. Okay, maybe I should have skipped this sentence. So, I will not let the climax too long. In fact, we can simulate these systems. We can compute the shape of the soap film. But imagine we could not. Imagine we discovered that this is one physical phenomenon that cannot be computer simulated. Then it means that we can use this device to build a new type of computer. Okay, there is now water and soap inside the computer. The water and the soap are part of the computer. And this computer could compute something more than the computer that we do have. It could compute Plateau surfaces, while our current computers cannot according to our hypothesis. So if we discovered a phenomenon that would not be that could not be computer simulated, it means that the physical Church-Turing thesis would be wrong, because we could use this physical phenomenon to compute more things, more algorithms than what we can compute with the current algorithms. So if you reverse this implication, you see that a consequence of Church-Turing thesis is that every physical system can be computer simulated. There is nothing on Earth that cannot be computer simulated. So at the beginning, when it was in the 30s, it looked like a very small issue. Okay, I have my language, your language, okay, they are equivalent, great, so maybe we have reached an absolute notion of algorithm. But now we see that this Church-Turing thesis evolved into a very strong assumption about the world, which is that every phenomenon in the world is can be computer simulated. So in fact, there are a lot of discussions on whether this thesis holds or not. And there is, for instance, a discussion on whether when we are approaching a black hole, the Church-Turing thesis still holds. In particular, because if you know a little bit of relativity theory, you know that time does not pass at the same speed, at the same pace for every observer. But when you're close to a black hole, what is a finite time for you may be an infinite time for another observer. So what the other observer would require an infinite amount of time to compute, you can compute it in a finite time. Okay, so you can compute more than a Turing machine, but you disappear in the black hole immediately. So it's okay, every has a price. Every problem has a price to solve. But if we exclude black holes, it seems that this thesis, this physical Church-Turing thesis, holds. So why do we know it holds? First, we don't have any counterexamples in physics. All the laws of physics are computable and so on. And then it's a consequence of another assumption that is made in physics, of two assumptions. The first one is that information cannot travel faster than light, which is a usual assumption in physics. And another, which is much more recent, which is that exactly like the velocity of information, the density of information is bounded. And this is called Bekenstein assumption. So, and from Bekenstein assumption, you can prove Church-Turing thesis. Of course, you can never prove it in an absolute way. You have to prove it from other assumptions. Okay, so we are in a kind of situation where when we assume this physical Church-Turing thesis, because now it has a relation to the problem that we were discussing at the beginning. And if you take another assumption, which is called materialism, which is that your brain is itself a physical system, and I will discuss this assumption a little bit later, then there is a syllogism. The syllogism goes this way. Every physical system can be simulated by an algorithm or a computer. Your brain, and my brain as well, are physical systems. Hence, conclusion of the syllogism, the brain, my brain, can be simulated by an algorithm, by a computer. So as always, when you have a syllogism, you can attack the syllogism, and there are various ways of attacking the syllogism. One is to say that the syllogism itself is not well formed. But in this case, the syllogism is well formed. I will say it again. Every physical system can be simulated by a computer. The brain is a physical system, so the brain can be simulated by a computer. So there is no mistake of logic there. But then, of course, you can attack each of the assumptions of the syllogism. And the easiest assumption to attack is the materialist hypothesis that the brain is a physical system. You remember the fourth line of argument at the beginning, we have a soul and the computers do not. So this is saying that the brain is not a physical system, hence the Church-Turing thesis does not apply to the brain, and this explains we have a free will, imagination, creativity, and so on. But you see that here, when you take the negation of materialism, it's called idealism, but you need a very strong idealistic thesis. Because it's not only that you have a soul, it is that your soul interacts with the brain and you can use your immaterial soul to think, compute, create, decide. So it's even my friends who are theologians, when we speak of cognitive sciences, they say the hypothesis of the soul should be put outside cognitive science. When we study how the brain views images, reasons, computes, speaks, we should not use this assumption that we have a soul. They are completely independent. And it is, this view has a name, it's called the non-overlapping of magisteria. Religion, soul, and science, brain, are both true, but they speak of something different, and they do not interfere. So if you want to attack the idea that the brain is a physical system, then you need to have this strong idealist viewpoint that contradicts this non-overlapping of magisteria. So you have to go very far in the idea that not only we have a soul, but the soul is active when we solve problems, when we do science, when we think about the future, and so on. So it's a very respectable point of view, but this is one way out of this idea that the brain can be simulated by an algorithm. The other way out is to attack the major premise of the syllogism, which is that every physical system can be simulated by an algorithm. And this viewpoint has been defended, for instance, by Roger Penrose. But it's not exactly the kind of hypothesis which is very economical, very thrifty. Because what Penrose says is that, of course, if we take the physics of today, which is general relativity, quantum mechanics, and so on, it's clear that every system can be computer simulated. But that we have to drop all this physics and to invent a new physics that will not verify this property. So of course you can imagine that everything we do in physics is wrong and we are going to drop physics and to replace it by a new physics. But it's a kind of expensive hypothesis. And especially Penrose gives no clue on where we should start with building this new theory, this new physics. So although Penrose seems to be very eager to do it, it's a respectable but not very frugal hypothesis. So if we don't go in these directions, if we accept that every physical system can be computer simulated, and a weak form of materialism that either we are pure matter or we are matter and soul, but the soul does not interact that much with the matter, then we are led to the conclusion of the syllogism that the brain can be simulated by an algorithm. So you remember that one of the languages to express algorithms had been invented by Alan Turing, had been proposed by Alan Turing in 1936. And the same Alan Turing, 15 years later, in his paper in 1950, had completely understood this consequence of the Church-Turing thesis. And in his paper in 1950, he takes the assumption at the very beginning of the paper that there is no reason why a computer, a machine, should not be intelligent. Okay, it doesn't use the word intelligent, but you see that you have in this paper, although you don't have the word, you have the very beginning of the idea of artificial intelligence. And artificial intelligence does not come from the idea of machine learning and so on as we know it today. It comes from this very idea that if we assume that the brain is a physical system and that any physical system can be simulated by a machine, the brain can be simulated by a machine, and then the question is, how do we know if a machine actually simulates the brain or not? So there is no reason to believe that a machine cannot act, speak, behave, think as us. And in fact, I think this is the main ethic problem that we are facing today. Because this idea that there is some singularity of human being, there is a thing that human beings do and that machines cannot do, is deeply rooted in our culture. It's called humanism. And if we drop this idea that we are different from anything else, we humans are different from anything else, then we are led not to transhumanism, and I will not use this word in this talk, but to post-humanism. We are led to think in a world where human beings are not that different from other entities. And humanism has been attacked in three ways. The first is what I have presented here, that a very elaborate conception of physics and its relation and the role of information and computation in physics lead us to think that in principle, although we don't have it now, in principle everything we do could be simulated by a computer. Then there is an empirical evidence that many things that we believed we were the only entity to do now are done by computers. So when Pascal invented his first machine computer to do addition, just to do addition and subtraction, people said, no, a machine cannot do addition, we can do addition. In fact, as you know, machines can do addition. So when Pascal showed his machine, people said, okay, a machine can do addition, it will never do a multiplication. Okay, then Leibniz gave a machine for multiplication. Okay, then people said, okay, but a machine cannot play chess. And in fact, in the 18th century, there is a fake machine that plays chess, but of course there is someone inside the machine that plays chess. But now, as you know, machines play chess quite well compared to us. But when Deep Blue won against Kasparov, people said, okay, but in fact, chess was a bad example. Chess is easy. A machine will never play Go better than we can. Okay, now, as you know, AlphaGo has won over Lee Sedol. Okay, so we can still continue and say, okay, multiplication, addition, multiplication, chess, Go, this was easy. A machine will never be able to translate text from German to French. And that's true that today, if you use Google Translate, it's funny. But can you be sure that a machine will never, after having failing 4 times, maybe we should be wiser. So we have lost this confidence that never a machine will translate better than we do. So this is the second reason to doubt from the humanistic postulate. And the third is ethology. Because as well as we compared men to machine, humans to machines, we compared humans to animals. And then we said, humans are the only ones to recognize themselves in the mirror. So there is a complete difference between humans and apes. When you put an ape in face of a mirror, it thinks it's another ape. And we know it's wrong. So how do you know that? It's because if you put some painting on the head of the ape while it sleeps, and you put a mirror, the ape should try to erase the painting on the other apes in the mirror, but it does that. So it means that the ape has understood that in the mirror it is self. So the apes, they have a sense of self. And in fact, the birds too. So the apes, they are almost human, okay, but the birds, they are dinosaurs, right? But, okay, not all birds, but some birds do, it's still discussed. And also we thought we were the only ones to speak. The animals were barking or shouting. But now we know that although the language of animals is not as complex as ours, they can, for instance, make different sounds to explain different types of danger, and the other animals know what it means and know how to protect from the danger. So if you have apes again and a lion, there is one way to tell the apes there is a lion, you should climb in the trees. And if there is an eagle, there is another sound to say, okay, you should go down because there is an eagle in the tree, so it's better to be on the ground. If there is a lion and an eagle, I don't know what they do. So, what we have to think today is how to understand, how to drop this humanistic hypothesis, but still keep the human dignity, which is a completely different topic. Human dignity is a concept in ethic, not a concept in science. So our notion of the human dignity, which is an ethical concept, rested upon this scientific, this epistemological concept of the singularity of mankind. But now we have to base our ethics on other grounds, on other postulates. And maybe we will build an ethics which will be monstrous. And let me give you an example. Once I was talking about that in a high school, and I told it would be good, for instance, that if we had the opportunity to save a human life or the life of a rabbit, we continue choosing the human life, which it's part of my ethics. It's one of the postulates of my ethics, is that if you, okay, so in ethics, the situations are always weird. So if you're on a desert island with a man and a rabbit, and the man is sick and the rabbit is sick, and you have only one dose of drug, and the drug works either for the man or the rabbit, but not for both because you have one dose. So this is the kind of typical situation we consider in ethics. I think you ought to give the drug to the human being. So I was explaining that to a 15-year-old students, and then one student tweeted that I was spacist, fascist. Okay, so some anti-spacists don't believe that the human life has more value than the life of a rabbit. I think it was a dog in my example, but whatever. And think that every life has the same value. I think this is a very dangerous viewpoint. But yet, we can also maybe build a better ethics, because starting from our humanistic assumption, we had the idea that the life of an animal was less than the human life, which is good, but zero. And the way we treat animals now, as you know, is more and more discussed, and more and more an issue, a controversial issue. And maybe this is because a computer has beaten Lee Sedol playing Go. Okay, because a computer has beaten Lee Sedol, we think, okay, maybe we are not so special. If we are not so special, then the calf, which is has not the same level of dignity as us, also has a level of dignity, hence we should not kill the calf. Okay, of course, it's a hypothesis because it's very difficult to be sure of anything here, but you see that this end of humanism is something we have to face, and we should take this opportunity not to build a worse ethic, but maybe a better ethics. Okay, some of my colleagues think it's a crime to switch off a computer, especially their computers. And it's a very interesting problem to explain why not. It's very interesting. Why isn't it a crime to switch off a computer? Okay, you have 4 hours. Okay, now you see that if we can simulate everything in the brain, we could, in principle, we can simulate emotion, we can simulate, I know you are going to ask a question about simulate, okay, but I don't mind. Okay, so we can simulate emotion, we can simulate creativity, we can simulate free will, and then our assumption that we are gypsy children completely vanishes, because everything can be simulated in what we do. So we cannot explain intuition, for instance, by saying that intuition is a purely human behavior, a purely human faculty that computers do not have. This does not hold if we assume Church-Turing thesis, materialism, and so on. We cannot say that. But of course, we have to explain what intuition is. We cannot just drop the concept. We have to find an alternative definition of intuition. And before that, we first have to understand why we are so uncomfortable with this idea that we are not better than machines. From a moral point of view, of course we are, but from a technical point of view, from a scientific point of view, we are not better than machines. And here, I think we have to explain where technophobia comes from. Because if we say we are not more clever than apes, we don't run as fast as lions, it's kind of okay. But when we compare humans, not to animals, but to machines, it's much more stressful, much more shocking. And I guess we have to explain where our technophobia comes from. And my hypothesis, and again it's only a hypothesis, it is that you know that in the European culture you have a division between the religious function and the productive function. You have people who are clerks and they spend all their lives praying, and there are people who are workers, producers, and they spend all their life producing things. And of course, the science and the technology belongs to this lower category, which is the category related to the productive function. And it does not belong to the religious function to which, for instance, the PTA belongs. And there is a very clear distinction between the PTA and the scientist. The PTA tells you, you know the PTA of Delphi? Okay? The PTA tells you tomorrow there will be an earthquake. The scientist tells you tomorrow there will be an earthquake. So far, so good, they are the same. To the scientist, you can say, how do you know that? Then the scientist has to give you a proof or evidence or something. The scientist, she has to say, okay, we did measurements of the temperature and whatever, and we have a model, and we know that the probability of an earthquake is more than 0.7. But if the PTA tells you there will be an earthquake, never ask how she knows it. She's a PTA. So the reason why she knows it is not because she has a proof or an evidence or she can explain on the blackboard why there will be an earthquake. It's because she's a PTA, period. So this is the separation between the religious function and the productive function. And we believe we are PTA. We are not happy to be scientists. And most of my friends who are scientists, they behave like PTA. Okay? They go on TV and they say, yeah, general relativity, blah, 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 and so on. Nobody understands anything, but they give an oracle. Take my friends. I have very good friends who are economists. When they go to the TV, they don't draw the equation. And, no, they say, if we do that, it's a disaster. PTA. Okay, now, end of the show. So, we have to deprive ourselves of this technophobia if we want to live happily with machines as machines. But still, we have to explain what intuition is, and to explain what intuition is, and maybe we have to explain what sophistication is, after all. So how to, first, intuition. We have an empirical evidence that we have intuitions. Okay? It happened to me at least twice in my life. I don't have a lot of intuitions, but it happened to me at least twice in my life that I wanted to solve a problem. I didn't have a clue. Then I saw the light. And I cannot explain how I saw the solution of the problem. It was a miracle. Okay, so this is an empirical evidence, and we have to explain it now. There is a kind of easy explanation. It is that there is a huge difference between able to use an algorithm and being able to express an algorithm. Okay, I did that with high school kids as well, not the same. I showed them 2 paintings of one painter and 2 paintings of another, giving them the names of the painters. Then I showed them a 5th painting, and I didn't tell them who it was, who was the painter. And they had to guess. And 100% of them guessed. Actually, I had put a lot of chance on my side, because I had taken early Renaissance painter of Italian painter, Lorenzetti, and New Yorker graph painter, Keith Haring. So if you confuse a Lorenzetti with a Keith Haring, really I cannot help you. But just with two pictures of each, they could discover by themselves that the 5th painting was Keith Haring as well. And just to tell you that we are very far from simulating the brain. If you want to do that with a machine learning system, you need 100 images. Okay, so you have to find 100 Lorenzetti paintings, and that's not that easy. Okay, so then I asked the students, how did you do? Can you explain me the algorithm to distinguish a Lorenzetti of Keith Haring? And they didn't know. But they were able to do it, but they could not explain me how I should do it. Of course, they said Keith Haring is brighter. Said, okay, what is bright? It's more colorful. What is colorful? Okay, so you can always try to give fake explanations. But the real thing is that in our brain, we have an algorithm to distinguish cats from dogs, knives from forks, and so on, and we don't know how it works. We cannot express the algorithm in a programming language, for instance. And if we want to program a computer to do that, it's very difficult. And in fact, on a finite machine, there is always an algorithm that we can execute, but we cannot formulate. Okay, so the more complex algorithm that the machine can execute, it can be executed by the machine, but it cannot be formulated. If you want to formulate the algorithm and then use the formulation of the algorithm to execute it, it's much more difficult than just having the algorithm wired somewhere in the machine. So we are every day using algorithms that we cannot formulate. And as we are in Vienna, I think we have to use the word, these are algorithms that are in the unconscious. And when I mean unconscious, I don't use the concept coined by the Viennese quack, as Nabokov used to call him, but the notion of unconscious as it's already there in Leibniz. And Leibniz tells us there are processes. Leibniz speaks about perceptions, but you can generalize it. There are processes, perception processes, that happen and we don't know that they happen. And it's the very beginning of this, or not very beginning, but it's one formulation of this notion of unconscious. And for me, how I recognize a dog from a cat is part of my unconscious. I can do it most of the times, but I cannot explain how I do it. It's unconscious to me. And maybe each time there is this algorithm running in my head and yielding a solution, but I don't have the energy, the force, the power to know exactly what happened in my mind, I call it an intuition. But it doesn't mean it's not an algorithm. It means it is an algorithm which is too complex for me to know it, too complex for me to formulate it. So this is what I call intuition. And then we come to the conclusion, which is what is sophistication? And again, we have an empirical evidence of sophistication. I know judges that do not care at all about the people they are judging. They just read the case, bike 1 week, car 1 month, truck 1 year, and that's it. This is what they do. And they really are sophists. But again, the question is not a matter of whether the good judge uses an algorithm or not, but whether the good judge uses an algorithm which is complex enough to take into account all the issues, context, childhood, goal, motivation of the people he has to judge. So it's a matter of complexity. It's not a matter of being a non-algorithm compared to an algorithm. It's a matter of complexity of the algorithm. And maybe also a matter of knowing which algorithm we use. If this algorithm is unconscious, then we think that we are less sophist than when it is conscious. If the algorithm is simple enough so that we understand it and it's conscious for us, then we have the feeling that we apply mechanically an algorithm. But if this algorithm is unconscious and we don't know exactly what happened in our brain and eventually we reach a conclusion, then we are not sophists anymore. And here you see that there is something which is often the case in science. In science, you have a box, and everyone tells you that you have to think out of the box. Okay, take an example. You know the whole numbers, 1, 2, 3, 4. Then a lot of people tell you, okay, invent new numbers. 1/2, square root of 2, -1, pi, I. Think out of the box. But from time to time, there are wiser scientists who say, but we don't know everything about the whole numbers. So we should think within the box and to try to use all the problems, all the solutions, all the tools we have in this box. And here it is exactly the same thing. There are people who tell you, okay, you have a notion of algorithm, but now creativity, free will, it's something else. While the wiser attitude, maybe, I don't know, maybe it's not that wise, is to say, okay, I have a box. Let's try to use the algorithms I have in my box and make distinctions between this algorithm, between easy algorithms, complex algorithms, non-deterministic algorithms, and so on. And this is enough to explain all the mysteries I have to explain, such as intuition or sophistication. So maybe sophistication is not the fact of using algorithms. It is the fact of using simple or over-simple algorithms. But if we use complex enough algorithms to take into account all the parameters that we have mentioned, then we should not call that sophistication anymore. It's still the use of an algorithm, but it's the best we can do. And here there is a question about finite and infinite, which comes into mind, which is that even if the algorithm takes a lot of parameters into account, everything that occurred in this case and in the life of all the people who are judged and so on, it will always be finite, while the human judge maybe can go to the infinite. In fact, I'm very skeptical to this idea that the human judge can take an infinite amount of information in his judgment. I am myself a little bit a judge because I have to decide who can study in my university or not. Actually, just in the second year of the master's, I'm not that powerful. And when I read a file given by the students, I try to take into account as many parameters as I can, where the students come from, what his previous grades, and what is the motivation, and so on. But then, of course, I have a finite amount of information in the file. It's a finite number of words, a finite number of letters, and I cannot use more. So it's the same for the judge. He spends 3 weeks studying the file, but he cannot spend more. So the information is always finite, like an algorithm. So, as you see, there is still a room for a condemnation for criticizing the use of simple algorithms, and I think it's good to call that sophistication, but it doesn't mean that we, as we say in French, that we have to throw the baby away with the water of the bath and claim that there are entities like human beings that are so sophisticated that they are non-algorithmic. Thank you.
Final round of statements and questions.
Thank you for your very interesting talk. What strikes me and what I would like to ask you is about your final question that I see how you elaborated. I think it's really interesting to say, to go on this very low level and to say there are algorithms as well and maybe too complex for us to understand. And on the other side, this glimpse that you brought when you said, okay, when you argued about the cognitive science, we said it's a strong idealist to claim for a soul. I mean, my question is just, if you go on this very low level, algorithmic level, why can't this be a soul? Why can't this somehow low level but actually high complexity can be thought in terms of a soul?
Okay, you have to ask a theologist. But my point was not to claim that we don't have a soul or that we do. I think we are not going to solve the problem tonight. But to focus on the argument that even if matter is ruled by algorithms or can be simulated, the material processes can be simulated by algorithms, this does not apply to human beings because human beings are something more which we might call a soul. So if you claim that the soul as well can be simulated by an algorithm, then you are not helping to solve the problem for which the soul has been introduced. In this context, the soul is not here for religious reason. It's just here because it's a common way to explain why there is a difference between Humans and machines, humans have a soul, machines do not.
Thank you. There is, I think what you were calling sophistication, I would call it sophistry. So there's a distinction between sophistication that we try to address and sophistry. And I think the distinction is actually very well laid out by your talk. But what I'm wondering from how you made your argument, is there for you a distinction between simulation and modeling?
Okay. So, I expected a question on the word simulation because one way to make a difference between a human and a computer is to say that even if the computer can simulate the human behavior, the computer does not have the human behavior. And it's very clear for emotions, for instance. You can very easily build a program that says, I'm happy, I'm unhappy, I'm depressed, and so on, as human beings. And human beings are very unpredictable. You never know why they are depressed or not, so you just take a random generator and the computer say, today I'm depressed, I'm happy, and so on. Okay. But of course, you say the computer is not really happy, it just pretends or it just simulates. And I also have a friend who is a psychoanalyst, strangely enough, and he pointed to me that in psychology in general, the word simulating is very negative. Okay, you can simulate friendship, you can simulate illness, but it's always negative. So that with computer simulation, we have transformed the world into something positive. But okay, let's do a thought experiment. I built a machine. The machine has a thermometer that measures temperature. Then if the temperature goes beyond one threshold, the machine activates another circuit, and the circuit activates pickup, CD player. Nobody knows what a CD is, but an MP3 player. And then the machine has a loudspeaker, and the loudspeaker says, it's cold, close the window. Okay, can you say that this machine feels the coldness? Of course not. The machine just is a thermometer, and it doesn't suffer, the machine. It's not cold. It just simulates being cold. Okay. But now, the machine I have described, in fact, it's you. Because the thermometer is your skin. This wire is your nerve. And this computing device is your brain. And this MP3 player is your mouth. So would you still say that you're not really cold, but you're just simulating? No, because this is what we call being cold. So if we do that for us, why don't we do that for the machine? Maybe the machine is really cold if it behaves in this way. So where is the difference between a simulation and a true feeling, a true act, a true action? It's exactly the question that Alan Turing asks in his paper from 1950, and he says intelligence, thought, whatever, is a purely phenomenological object. There is no noumen of feeling, thinking, acting. If the machine from the outside, you cannot make a difference between the machine and a person, you have to say that the machine thinks, feels, resent, because it's a pure phenomenon. And the nature of the process which is inside the machine, whether it's a biochemical process or an electronic process, it's none of your business. If you can talk to the machine, it talks. if it answers, you should not say the machine simulates talking, it talks.
But my question was with regard to simulations that are used for making predictions. No? So you are always answering and also developing your arguments as an ontological argument. So can machines be like humans? How can we make the distinctions? That's precisely what I want to bracket with the interest in sophistication, because in sophistication, coming from having a relation to sophistics, it is unproblematic that it works with schemata, that it works with mechanisms, that it works ultimately with things that it cannot reason and doesn't understand, but it knows how to use it, and by knowing more or less how to use it, you can more or less create a situation that is more or less predictable and anticipatable. So this is, and for what is interesting with us, with this interest on sophistication, is exactly that scope that opens up of deliberation, which cannot anymore be one of a logical decision. Yes, no, is it more true, is it not true, does it belong here, or can we not say? That is in a way becoming much, much, much less interesting. And the question is how then to address this kind of responsibility, no? By affirming to work with algorithms, by not caring whether it is a human thought or an algorithmic product and so on. And with regards to this, I was asking you whether for you there is then a distinction between modeling and simulation.
Okay. So I will answer this question. Before I do that, just a digression. The question of the responsibility is itself a very difficult question. So can an algorithm or a computer be accountable, liable for something? But okay. So, but I said I'm just mentioning the problem to say I'm not going to address this problem. Okay, so first, modeling. We have theories that are predictive theories. And we have, for instance, theories in physics or in biology that are predictive. Let's take physics and chemistry, because it's enough to see the difference. In physics, most of our theories, they are expressed as differential equations, Newton's law and so on. But it's not made in the notion of theory that the theory has to be a differential equation. It's one way to express a theory. What is a theory? It's something that permits to do prediction and maybe to explain the phenomenon. Okay, but let's focus now on making a prediction. There are other situations where we can build we can phrase a theory that still permits to make prediction without using differential equations, without using the propositions of predicate logic, without using propositions at all. And it is a case where we build a model, and a model is just a theory, like the theory expressed with differential equations, but expressed in a different language, which is an algorithmic language. So we have a model that predicts earthquakes or the temperature it will be tomorrow. There is no propositions in this theory, but the theory itself is expressed as an algorithm. And this is what I call modeling. Now, is it different to simulate an earthquake or to model the movement of the Earth, of the plates, not the Earth itself? I think there is a difference, which is that in one case, you use the algorithm as a language to express something, to express a relation, and you express it in an algorithmic language. And in the second case, when you actually simulate, you execute this algorithm. Okay, so in one case, I tell you, there is an algorithm that relates the RNA and the protein, and this is modeling. And in the other, you take this algorithm and you execute it to get the description of the protein. And in this case, you're simulating. So the simulation is just the execution of the model, while the model itself has a descriptive virtue, a descriptive value, before it can be executed. And in fact, if you look in the history of science before the computer age, the fact that the theory is predictive, or the fact that the theory is more than a description, but it permits to compute a prediction, is hardly mentioned. We have the theory, which is seen as something which is completely descriptive, Newton's law, Maxwell's equation, blah, blah, blah. And of course, we use them to solve problems, to do predictions, but the value, the virtue of the theory is in the description. And maybe now we understand that a description that would not have this ability to make prediction would not be of a very high value. And you see that there is here a thread from, let's say, Carnap, Popper, and models, where the importance of the prediction was more and more put forward. So, did this answer your question? Maybe not.
For me, it was an interesting talk, but I'm puzzled, I think, at the same point like Vera. So my question, or what I'm interested in and how you deal with it. So in my understanding as an architect, quantum physics, for example, and by that computer technique is not a physical system. So by that, quantum phenomena are out of the Church-Turing thesis. So you can't simulate it. So what do you say to that?
Okay, so there are two questions. The first one is about simulating quantum systems. And of course you can simulate them. There is no problem in simulating quantum systems. We do that every day. Oh.
This is orthogonal. So I think this is what I understand with quantum physics. This is axiomatic, and in my understanding, a system is atomistic, and this is orthogonal to each other.
Okay, so if you have a descriptive system which is given by a differential equation, for instance, then we know that the solutions of the differential equation, they are computable functions. And we even have an algorithm to compute them, which is for simple equations, Euler methods, but of course there are more complex algorithms for more complex equations. So the fact that we have a descriptive theory does not forbid us from building an algorithmic theory on top. And in fact, usually the description is close enough to an algorithmic description, for instance, when we have differential equations, so that we can use it for predictions. But here, there is nothing specific with quantum physics. You could say the same thing for Newtonian physics. Newtonian physics, it's descriptive, but still we can use it to do predictions. So maybe you should point out one specificity of quantum physics that Newton physics does not verify that motivates your question, which is that quantum physics is non-deterministic. It's a purely probabilistic theory. So you cannot predict, neither compute the future of a system. But of course, if you take a non-deterministic theory like this, you have to simulate it by a non-deterministic algorithm. You cannot simulate a non-deterministic physical system by a deterministic algorithm. This will be pointless. What does it mean to have a non-deterministic algorithm? It is either an algorithm that just computes the possibilities in which the actual system will evolve. So this is what usually we call a non-deterministic algorithm. I think you know what a non-deterministic automata is, and you know the way to determinize a non-deterministic automata by computing a set of states. Okay, it's exactly the same idea. And then in the case of quantum physics, you have more, because not only you can compute all the future of all the possible future of the systems, but you can equip all these futures with probabilities, and the probabilities themselves are computable. So not only you're able to say the system will evolve to A or to B, but not to C, but you can say the system will evolve to A with a probability 1/3 and to B with a probability 2/3, and this is what we call simulating a quantum system. You cannot do more, of course, because the theory itself is non-deterministic.
Huge space for a new kind of humanism, huh? Beyond this.
No, I don't see the relation. Okay, sure. Your second question, I'll be 1 minute on this second question. I completely agree that the computer itself can be seen as a non-material object. So why? Because if we take the same algorithm, the same program, even the same computer, we can build it in many different ways. And as computer scientists, we are used to consider that the way we build it is immaterial, the way we build it is not important. It's easier in French, but in English it's a trap. Okay, so, and then we think as a computer as an abstract object because its implementation is not that important. Okay, so this is one abstraction that we built in computer science, which is a very good and very useful and very beautiful abstraction, and this is what I teach to my students. But as with every abstraction, we have to be able to think at different levels of abstractions. And one day, the computer has to be built using either photons or water or silicon or whatever. And once you have built it using any technology that you want, then it's a physical system, and then the physical Church-Turing thesis applies to it. So you have to break this abstraction to be able to understand this limit of what you can compute. And this is what physics of computation is about. Okay, sorry, I delayed your question too much.
I want to make a comment because your description about physical systems was mainly referring in terms of differential equations. So basically, classical physics, but even there, we do not have a solution of the four bodies problem. As you know, there is only an exact solution about 3 bodies. Now, if we move to the domain of dynamical systems and nonlinear dynamics, when we have a phenomena of chaotic behavior, differential equations do not work. We need topological models of stability and so on. In quantum mechanics, we have now topological states of matter which display hybrid behavior, for example, topological insulators, where they can insulate from the inside and outside behave totally different. In all these cases, we encounter the phenomenon of self-reference. And the human mind can perform all the time in the domain of self-reference, whereas the function of a machine breaks down exactly on this domain. So how do you think, what is the canonics which would bridge the human with the artificial intelligence?
Okay, so there are many questions in your question. So usually I have 2 questions. One is about quantum physics and the other is about chaos. So let's speak about chaos. I will not go to too difficult chaotic systems. Let's take a very simple chaotic system like the Baker transformation. So just to explain you a little bit what the Baker transformation is, if you don't know what it is, I think many people in the room know what it is. But if you think of a baker that is rolling the dough and then folding it and then rolling it again and then folding it and then rolling it again and folding it many times, then you can consider 2 very close points, 2 very close grains of flour in the dough. And at the beginning, they are just 0.5 millimeter far one from the other. But when you roll the dough, then they become at 1 millimeter, then 2 millimeter, then 4 millimeter, then okay. So a very small difference at the beginning makes a huge difference in the end. Okay, so this is why many systems are unpredictable. Okay, unpredictable in what sense? It means that if you have a finite amount of information on the position of the point in the DOE at the beginning, then your uncertainty on the position of this point through the transformation increases and increases and increases and increases. Okay. So this is what we call the limit of prediction in a chaotic system like the DOE being rolled and folded. Okay, now what does it mean for function mapping real numbers to be computable? It means that if you have potentially the infinite digits of the position, you can compute the infinite digits of the position after the transformation. And then you can iterate that, of course. And what we call computable function is a function such that for each number of digits you want on the result, there exists a number of digits in the input that is sufficient for an algorithm to compute this approximation of the result in the result. And this is exactly the property that the Baker transformation verifies. So the Baker transformation is unpredictable, but it is computable in this sense. And you can even see that it is unpredictable, that it is chaotic in the structure of the algorithm, because the structure of the algorithm is that of a greedy algorithm. The more you iterate, the more you need digits on the input. And this is what we call chaos. So for a long time, in chaos theory, they used the word non-deterministic. Then they changed completely the vocabulary, because now this is called deterministic chaos. So it's deterministic, but it's not predictable. And they even put the adjective deterministic to say that it's non-determinism. And I think it is the same thing we should do with the adjective computable. We should call it the deterministic computable chaos, because it's chaotic, but it's deterministic and it's computable. Okay, so this was the first question you had. The second one is whether we can imagine whether physics will develop in such a way that at some point the physicist will introduce a theory that is non-computable. And this is a possibility that remains open. And if they do, I would be very happy. Why? Because as I explained with the example of plateau surfaces, if we find, and with the example of black holes, if we find a phenomenon that cannot be computer simulated, then we will have a new kind of computer using this theory, using this behavior of matter, using this feature of the new theory. And this is exactly what Penrose claims, hopes, wishes. And if we have such a discovery in physics, then it will be a complete transformation of computer science, because we will have new computers that do something completely different. But for instance, the so-called quantum computers that use the most classical form of quantum physics, not quantum gravity, just quantum physics as you learn it in high school or maybe in university, in for a bachelor degree, then it does not have this property. Quantum physics is completely in the same realm as Newtonian physics, as relativity theory. It's completely computable, and there is no such phenomenon. So if you tell me that in a paper published yesterday there is such a phenomenon, let's celebrate.
Already observed topological states of matter,
okay,
which have hybrid behavior, so they cannot be simulated on a universal Turing machine. Already we have this.
Okay, so if there is this proof of undecidability of, if the theory permits prediction that are undecidable, then it's I would be very happy to read the undecidability proof. If you can encode, for instance, the halting system, the halting problem in such a system and solve it in this way, it would be a big step forward. So far, I have not seen any theories like this. At some point, quantum theory was proposed, general relativity was proposed, chaotic systems were proposed, and each time it happened not to cross the Turing barrier, but if it does, it's right.
Okay, I think we are...
Vera has another question?
Yes, I hand over to Vera. Thank you.
I try to get back to my question from another side. So if you don't make a distinction between, with regard to the problem of representation or of adequacy in the description, or if you're not claiming that the simulation helps to clarify the adequacy of a description, if you simply presuppose a description with which you work, which you apply then basically in the simulation. But then doesn't this mean that one can equally well produce evidence through simulation for a rumor, let's say, or for a completely fictitious assumption, if it is formulated in terms whose description is loose enough that one really needs probabilistic speculation in order to substantiate it? Wouldn't we completely lose the distinction between a produced evidence on the level of simulation, algorithmic demonstration, and so on, of something that is actually describing something, and something that is actually calling into being something which is sophistic, no?
Yeah, so, yeah. So. Okay, so now I guess I understood the question, but there are three questions. Okay, so the first one is whether when you have a theory, whatever the form in which it is expressed, like differential equation, algorithms, and so on, then the theory has to be powerful enough to make prediction, and we have to be able to compare the prediction with empirical data, and we should not find a mismatch between the prediction and the data. So this is the notion of quality of a theory, and this is a very important property, as we know since Popper at least, but also since Wiener Kreis. And in the case of an algorithmic theory, we are closer to have predictions because we just need to execute an algorithm, which is simulating the phenomenon. So I didn't claim simulation was not important. I think it's very important because after formulating the theory, there is a second step where we have to compare the theory to nature, we have to confront the theory to nature, and and to do so, we have to be able to execute the algorithm. What I just wanted to point is that sometimes we have the algorithm, but we cannot execute it because it takes years or centuries or so on. So the algorithmic description should not be confused with the actual possibility of executing the algorithm. So this was the first point. The second point is that with models and with theories that have a huge number of parameters, and some of them have an infinite number of parameters, then this confrontation to reality is much more difficult. And let's take a simple example where you have only one parameter, which is the law of gravity. If you take the law of gravity as Galileo formulated it, the speed of an object, or let's say the distance traversed by an object, in a time t is 1/2 of g, which is a constant of gravity, local constant of gravity, times the square, multiplied by the square of times. Okay, so there is a parameter, which is this constant of gravity, and if we have just one observation, we can always adjust the theory so that it fits this explanation. It fits these observations, because there is always a value for the constant, g, the parameter of the theory, which will make the theory agree with the observations. Fortunately, if the theory has only one parameter, and we have two observations, then this is not always the case, and we can refute a theory even if it has one parameter left. The problem that we have with the computational models is that they, instead of being written on one line, like Maxwell's equations or Newton's equations and so on, they are written in thousands, millions of lines. They are huge algorithms, huge programs. And in these theories, you have a lot of parameters. So even if you have a lot of observations, your model is so flexible that you can adjust the parameters of your models to explain the observation that you have made. And this is a weakness of this way of describing external phenomena. Because if we have a two plastic theory, then we can always find a solution to match the observations. So when you have a huge theory and a scientist who tells you we have 100 observations and it matches, always ask how many parameters do you have in your theory. If you have 1 million, then it's not too difficult to be in accordance with 100 theories. Okay, the last point that you mentioned is about, let's say, fake news. So if we drop descriptions, propositional descriptions with propositions, and proposition can be true or not, and we replace that with algorithms which are purely operational, and the notion of truth of a proposition is not as central as it used to be. Okay? And this is a danger if we are not used to this notion of truth, that we may lose the very sense of truth and believe in anything. And it's something that we all face in it's an ethic dilemma, whether you should lie for a good reason. Okay, so it's a very old ethic dilemma. So maybe there is a fake news that will lead you to vote for Donald Trump, which is a very good idea, according to me. So I say, who cares about the truth of what I'm saying? What matters is your behavior, and if I can change your behavior for the good, according to my values, then I should do it. And this is one danger that we have if the notion of truth is not at the center of our epistemology, but the notion of computation replaces the notion of truth at the center of our epistemology. Okay, but there is a way out. It is that when you design an algorithm, you neither design an algorithm just by itself, alone. You design an algorithm which is a non-propositional object. It's not, an algorithm is neither true nor false, but you design the algorithm with a specification. And the specification, it is a proposition. If you take the example of algorithm I gave at the beginning of the talk, I told you we have to design an algorithm to find a word in the dictionary. And then the question, does my algorithm find the word in the dictionary if this word is in the dictionary, is either true or false. So even if a little bit of algorithm seems to put the notion of truth as a secondary notion, where the notion of execution becomes the primary notion, more algorithms or more complex algorithms put back this notion of truth in the development, in our scientific processes. So we should be optimistic. Does it answer your question this time? Now you can reformulate.
I think it's a good final statement. Let's be happy and let's keep to think about sophistication. We will have a next conference next year. And I would, again, very much like to thank you for the talk. As
I am the last speaker,
you are the last
it's
speaker.
My joy and my duty to ask everyone to thank you for organizing this wonderful meeting.
Thank you.